I'm Simon Foucault from the Department of Mathematics, and so I'm very happy to introduce on behalf of so TAMIDS and also CAMDA, the Center for Approximation and Mathematical Data Analytics. So to introduce Justin Romberg, who's the Schlumberger professor and also associate chair for research in electrical and computer engineering at Georgia Tech. He is also one of the director for the Center for Machine Learning there. His research interests are in well, imaging, inverse problems, data compression, sparse approximations, and many things. He was in fact at the heart of the explosion of activity in compressive sensing back maybe 15 years ago now, in particular with some very influential papers with Candace and Tao. He has received several awards, prestigious ones like the ONR Young Investigators Award, the Pegasus Award. In 2018, he became an IEEE Fellow. In fact, he was an associate editor for IEEE Transaction on Information Theory for quite a while. And more recently, he's also an editor of the Science Journal for Mathematics of Data Science. So a little less unusual, he's also been a consultant for a TV series called Numbers. I'm just going to finish by mentioning that Justin has some link with Texas because he has spent, as I understand, about 10 years at Rice University. And with that, Justin.
Thank you, Simon. Yeah, it is a shame I can't be there. I was just talking with Simon before everyone came on. So as you can see, I was supposed to visit on March 16th, which was right when everybody was in complete freakout mode. So we decided to delay a little bit. But I do, miss out on this chance. I mean, like now I'm still doing the hard part here of giving this talk, but I don't get the fun part of visiting with everyone and like, seeing what everyone's up to. Okay, so, I am actually going to talk today about kind of a new research area. I basically one of my ex-postdocs and graduate students sort of got me into. It very much uses some of the expertise I developed about randomness over the years, but it's a sort of new problem set for me, kind of like optimal control and machine learning. So we're going to talk about the decentralized stochastic approximation and optimization, and especially how it applies to the multi-agent reinforcement learning. So this is kind of a mix between almost like distributed optimization and reinforcement learning. Okay, so a lot of this talk. So okay, yeah. Before I go on, I should mention the key people involved here. I'm sort of the coach for this project. The intellectual vision for much of what I'll say here is really due to Tin Doan and Sihan Zheng. So Tin was a postdoc at Georgia Tech who worked with me and Sivatheha Maguluri, who's an assistant professor in our industrial systems engineering department. He's now an assistant professor in EC at Virginia Tech. And Sihan Zheng is a very talented graduate student, a sort of mid-career graduate student here at Georgia Tech in ECU. Okay, so with the nature of this talk is going to be very mathematical, but it's mathematical questions that have let's just say a certain amount of hype around them right now, right, or a certain amount of excitement, if you will. Okay, so this, there's this exciting field of reinforcement learning. It's actually sort of a very old field. It's always sort of intimately linked with optimal control. Always had a place in engineering departments, especially in electrical engineering and aerospace engineering schools where control problems play such a huge role. But there's been these, part of this sort of machine learning revolution has included applying sort of reinforcement learning to exciting new problems. Right, so I guess very generally, we'll talk very carefully about how reinforcement learnings are formulated from the mathematical point of view, what particular problems you can take from them. But very loosely speaking, what reinforcement learning is, it's a sort of framework for solving like sequential decision-making problems. right? So basically I have a kind of process, and I make a decision, and the decision I make affects the sort of rewards or observations that I make and the decisions that I can make subsequently. Okay, so there's all kinds of scenarios you can fit into that kind of general framework. Like one is like, okay, playing the game of Go, right? I'm sure if you've heard anything about machine learning in the past 4 years, you've heard of this, massive supercomputer trained on a neural net who used as much energy as it takes to fly back and forth across the country many times, 300 times, to beat the world expert at Go. Again, this was solved in the context of reinforcement learning. Here it's like you have this sequential decision problem, but like kind of the key aspect is it's very hard to predict, or maybe you don't have an exact model for what comes next, given that I take a certain action. That could even be like in this case, the state space is so enormously large, I can't quite consider everything, or there just could be some inherent uncertainty in what's going on. Like other examples include like, okay, these ideas of kind of experimenting to figure out what an optimal decision sequence might be. They've also been applied to like, having robot arms manipulate things in a subtle way, which is again an extremely hard problem and control to solve analytically, but if you sort of solve it from this idea of experimentation using this framework of reinforcement learning. In particular, what we'll talk a little bit about too is this idea of like distributed reinforcement learning, where here you have teams of agents operating cooperatively to achieve some goal. So like on the bottom right here, maybe you're trying to achieve the goal of navigating down the highway in a timely and safe fashion. Maybe on the left here, you have the goal of like, having a team of drones try to explore a region, again, cooperatively. Okay, so at a very high level, like these are the types of like applications we're motivated by. But like I said, even this field is so exciting, has gotten so much attention. There is a very solid mathematical underlying to all of this, and there are surprisingly some very important open questions about that mathematics. Only some of which I'll talk today. And really what these mathematical questions revolve around are things like we've gotten used to asking in the field of optimization, like how long does it take for me to learn something, right? When can I guarantee that I've learned something optimal or near optimal? So those sorts of questions, of course, a lot of things are classically known about convergence, but what you don't know is this kind of like, how many samples does it take me to converge? So that's kind of one of the things that we're after. Okay, so again, like we'll treat everything from the equation standpoint, but we'll also, since I know not everyone has a background in reinforcement learning, and I really even didn't until 2 years ago, I really want to be careful in just setting up and impressing on you like what the kind of like real mathematical problems are here. Okay, so ultimately, the ingredients will combine. They're all pretty simple, except for the analysis part. But I think they can be understood in the process of a couple minutes. So, this distributed reinforcement learning we'll talk about, it's really a combination of 4 different things. So this idea of stochastic approximation, right? We'll say exactly what that is in a moment. But basically the idea is you're solving, it's a way to sort of iteratively solve a system of equations, possibly nonlinear system equations when there's noise involved in the procedure. And it's intimately related to doing like stochastic gradient descent for optimization, but it's not exactly the same. Markov decision processes, this is basically this formalization of this sequential decision-making framework. Writing down like what do we really mean when we say we make a decision and we get a reward, et cetera. What is the exact framework for that? Another ingredient is something that's like very natural, I think, to most people on this call. So this idea of representing a function. This is basically just a basis expansion as far as we'll use it. Again, it's for anyone that has any kind of background in harmonic analysis, this part is super easy, so we won't spend too much time talking about it. And the last idea is the idea of network consensus. So we have teams of things trying to cooperatively, I'll just say, figure something out, learn something. and they all want to share information with each other in the right way, so they come to sort of the same global understanding or global solution. And so there's this idea, and we'll see this eventually, is with that we're able to do this without any kind of like central coordination, using this idea of network consensus. So again, it's a very sort of simple idea, but it allows us to do some powerful things. Okay, so what I want to do is sort of talk about these components one by one, because I think it'll help you appreciate like what the mathematical problems are here, like how these are set up. Okay, so let me talk about stochastic approximation. Of course, I don't want to no one's to be disappointed. There is going to be some complicated probabilistic analysis involved in all this. I will spare you the gory details, but I will talk about like some of the real tools you have to use to get like concrete statements here. Okay. Good. So let's talk about this stochastic approximation first. Okay, so the starting point is, I think, probably something most of you are very familiar with. Let's just say the Banach fixed point theorem. So all this says is if I have a mapping that goes from Rn to Rn, so it takes a vector, spits another vector out. If this mapping is a contraction, right, all that means if I look at the difference between the mapping applied to two vectors, right, it shortens the distance between those two vectors. It doesn't matter what this norm is, right? I'll just say it's the L2 norm, right? And so if this shortens the distance means this is some multiple of the original distance, where that multiple is some number less than 1, or can be bounded by some number less than 1. Okay, so then, we know that if this is true, there is exactly one point that is a quote unquote fixed point, where if I apply this operator H to this X star, I get X star. Right? And not only that, there's kind of a very straightforward algorithm for getting it. What I do is I just start by applying H to some number. I take the output, apply H again, take the output, apply H again, etc. Right? So it's a standard fixed point iteration. And under these conditions, the limit of these will be X star. And then, the X star being this fixed point. And in fact, this is not a difficult thing to prove. Don't take this as a proof. This is not quite a proof that's on here. What I'm saying is not only does that happen, it tends to happen very quickly, right? So if I just look at this equation, I say, okay, let's just say a fixed point exists, right? So here it is. Since this is a fixed point, I can just replace that by H. And then I just apply this contraction property, and I see that at every step, right, what I'm doing when I apply this H, I'm getting a factor of delta closer to this X star in whatever norm this is, right? So that means after K plus 1 steps, I'm delta to the K plus 1, a factor of delta to the K plus 1 away. So it's like, long story short, like not only do you converge, this convergence is geometric, right? It happens very quickly, which is very nice when you're talking about algorithms converging. Okay, so that, I'm sure many of you have background in this. If not, I think again, the only point here is like you're iteratively applying the same operator again and again, and it goes somewhere and settles there. Classic or super important example of this, right, is when this is kind of like this mapping is a gradient descent step, right? So I can set this mapping to be the current point minus some multiple of the gradient at that point. And then what this is doing is exactly gradient descent. Right, and if I find a place where h of x equals x, what does that mean? It means the gradient is 0, and I'm at a stationary point of this function. Or if the function's convex and maybe it has certain smoothness properties, I'm at a globally optimal solution, and maybe this is a contraction still, and this converges linearly, and there's a lot of analysis and optimization kind of geared toward that. Right, so this is only to point out that like this idea of a fixed point iteration is again, it's central to the way not only we think about reinforcement learning, but just optimization in general can be thought of through this lens. Okay, good. So that's that's the basics fixed point theorem. Okay, it's also true, just this because this is what we'll have to use later, that I can be sort of conservative, right? I don't have to take xk plus 1 is just equal to h of xk. I can take some, say, combination of or some convex combination of my old point and h applied to this, and I still get this geometric convergence. It just so happens to happen a little more slowly, right? But doing things like this happens to be more convenient and stable when there's uncertainties involved. Okay, So this is just another form. The point is here, this is just another form of the fixed point iteration where you're kind of, you're taking some combination between what came before and what H is fitting you back. Okay, so what at the core for reinforcement learning, really what you're interested here is fixed point iterations, but there's inherent uncertainty involved. And I'll talk specifically about where that uncertainty comes from. But for now, let's just say we have a very similar setup, right? Where we have this type of fixed point iteration, but instead of getting an HK back, when I take this XK and I plug it into my mapping H, I also add some noise to it. So let's just say the expectation of the noise is 0. You can say the noise is independent for now, but even that won't even be a condition we have in the end ultimately. Right. So now what happens, you can see like, okay, now if I say run these iterations, right, I can see that I'm not going to converge, right? I know that like, even if XK happens to be a fixed point, even if it happens to be X star, right, adding in this noise is going to move me off of X star. But what you do is you do like go and you do converge to a ball that's close to the solution, right? And so the random noise causes you to oscillate inside this ball, and like the width of this ball depends on what this factor alpha is, and maybe what the second order statistics are of this noise, et cetera, right? So the fundamental thing here is when there's noise, you converge to this kind of ball at exponential rate, and then you oscillate inside this. Okay, so then I think in the 50s, it was realized that there's a way to actually get this to converge, this result by Robinson and Monroe. So what they do is you say, I can drive, even when there's noise, I can drive this to a solution by changing this step size alpha k. This, how much do I take of this kind of innovation versus where I'm already at. Right, and what was nice, they said, okay, if you choose these step sizes carefully, what you need for them to go to 0. So the sum of the squares have to be less than infinity, but they can't go to 0 too fast, right? So if I just sum them, it's equal to infinity, and these are always positive things. Then what basically this condition, so this condition sort of sum of the squares going to 0, that allows you to basically get rid of this term ultimately and arrive at a fixed point, something like a fixed point, not move. And what, making these terms big enough it kind of allows you to average out this noise from iteration to iteration, right? So you can kind of see how it's like, oh, give these perturbations are all different for different K. If I just take a little bit of the last one, average into what's here, they start to average out, and you can average things out so you get to the solution. Again, and say you take alpha K is like something like 1 over K. Then you do get kind of a much slower 1 over K type of convergence, again, under just certain conditions on H to this fixed point X star. So the point is like this idea of a fixed point iteration, this works nowhere near as fast, but it does work when there's noise. And again, if you think of HK being some kind of like gradient descent map, this is often the lens through which like stochastic gradient descent is analyzed in machine learning. Okay, so that's just background on stochastic approximation. So, I mean, as you can guess, we'll be sort of interested in how quickly iterations like this converge, but we'll be interested on the types of equations that come as part of this reinforcement learning process. Okay, so to understand, it's actually, you can understand really quickly how these type of iterations come up just by looking at how problems in reinforcement learning are formulated. So the formula was something called the Markov decision process. There's a couple symbols I'm going to flash up on the next slide, but I think ultimately the idea is very intuitive, and you can see like what it has to do with sort of sequential decision making. Okay, so let's just say like here's the general framework, and to explain this, I'm going to use this picture on the right, where there's this little airborne drone here exploring an interior space, right? And so this is a kind of a cool picture, but to go with a kind of very mathematically concrete set of words, right? So, okay, here's what we mean by like a Markov decision process, right? So, we have an agent that's just the thing in charge of making the decision. It finds itself in a state ST. So in this case, maybe the state is the position in the room, but more likely, maybe what the state is what I'm seeing through my video sensor, So it's maybe it's this, this thing down here in this purple box. This is a picture of, what this drone is seeing from its forward-facing camera, right? So this ST is this collection of colored pixels, right? And that's the input that I'm gonna make a decision about, make a decision what to do based on. Okay, so then based on this state, right, it takes some kind of action, right? And so basically in this case, you can think of the action as, oh, should I move up? Should I move down? Should I move forward, left, right, etc., right? And then, given that you've decided to take this action in this state, you move to a different state, and maybe there's some uncertainty involved in how you do that, right? And so I guess that again, if you think back to, okay, it's like this is what I see. If I move to the left, what am I going to see next? Maybe you can't quite describe that exactly, but maybe you have a probabilistic model for it, right? So that would be something that very naturally falls into this framework. Or it could be like maybe you know exactly what you'd see next, but the dynamics themselves are uncertain, right? When I push this lever, sometimes I go to the left, but sometimes I go to the left, a little bit up, et cetera. So there could be like uncertainty comes from the physics itself. Okay, and then like the whole the key part of these decision processes is whenever I take this process, I'm in a state, I take an action, I move to another state, I get some type of like reward. And that's just to sort of, all that is sort of some kind of feedback about how effective taking that action, taking action AT was in state ST, right? So maybe it's like, here, maybe you get a reward of +1 if you manage to move to the next state without crashing. Maybe you get a reward of -100, if you don't achieve that and you find yourself upside down on the ground. Okay, so those are the key elements. There's this, the way we denoted things, we're talking about uncertainty being in this transition of moving from a certain state to a next state, given some action. There could also be uncertainty in the policy. So if I say like, given this state, maybe I use that state to define a distribution from which I draw a random action. That's something actually will come up in a little bit. And also could be these rewards uncertainty. There could be some randomness in these rewards. So there's lots of opportunity for building on uncertainty in all these places, and it doesn't change the central story too much. Okay, so here's one thing you're interested in where like fixed point iterations come in. So one thing you're interested in is, let's say I have a policy. And basically all policy is when I'm in a certain state, I take this action. And I want to say, how good is the idea, is it, right? Maybe I have a policy that says, well, I'm right next to the wall, I should fly into the wall. And that's a bad policy. And if I'm right next to the wall, maybe I should move away from it. Maybe that's a better policy. But, given this kind of well-defined mapping, how do I talk about how good it is? And the way you do this is you say, okay, like what I say is like, if I start in a certain state S, and then apply this policy from then on, right? What is sort of the long-term reward? So it's the sum of all the future rewards I get in this kind of Markov chain, where each state is determined through an action. The next state is determined by a well-defined action on the last state. And then this gamma T here, this is what people call the discount factor. So, what it means is like, I'm going to be kind of greedy in that, like, I want current rewards to count more than like speculative rewards that might happen in the future. That's a nice modeling story, but honestly, like having this kind of thing in here helps sums converge in the right way, and like makes a lot of the math work out. So we go with it. Okay, so this is what we mean. Like, this is sort of the long-term reward of this policy, and this is a function of the state. So, starting in different places, I'll have different long-term rewards. And so one fundamental problem is like, if I give you this policy, can you tell me what the long-term, what the value is for this policy, this value function for the policy is? Okay, and so now there's one sort of key thing. It's that, if I sort of expand this expectation here, with again, the only thing we're sort of considering is that are random are these dynamics, these transition probabilities, but there's all other ways you can take this expectation as well. Because we have this kind of Markov structure where, of course, this value depends on the starting state, and that state affects the trajectory from there on after. And of course, that dependence gets weaker as you move on to the future, right? But, you know, it also means that, okay, if I just, consider starting at like state S3, I don't really have to worry about S1 and S2 versus S4 on, right? And so that kind of Markovian structure results in what's called the Bellman equation. I mean, this is so important in control. It's sometimes just referred to as the principle of optimality. And it's basically like I can figure out the value, the value function, whatever it is, it should obey that, I can decompose it as the expected reward of a single step plus gamma times the reward of whatever comes after, whatever state I transition to, right? And so that's basically what this is saying. And then if you step back for a moment and look at this, you say, okay, like this is, on the left here, I have this vector v mu. On the right here, I have this vector v mu. Honestly, all we're trying to do is find a v mu that satisfies, in this case, even this set of linear equations, right? And so ultimately what this is a fixed point equation for this policy function. So I'm sorry, this value function. Okay, so, we talked all of that stuff about fixed points. Here you see exactly how, okay, once I put myself in this sequential decision-making framework, immediately what pops out is this fixed point equation. Okay, I should also mention, because something will come later, another thing that people like to keep track of in this context of Markov decision process sees is something called the Q function. Basically what this is it says, okay, what is the long-term reward using this policy of when if I start in the state S, so S naught equals S, of taking a certain action at the beginning and then following that policy from then on, right? And again, there's an associated Bellman equation with this. And this is essentially, what kind of the point of this is that it literally allows you to judge the value of the policy, because you could say, okay, I know what the long-term reward is taking this action. How does that compare to the action my policy tends to take? So this function is usually kind of plays an integral role in figuring out how to perturb policies to make them better. Okay, so again, you can this just by the same sort of principle optimality we talked about before. There is a recursive equation that the sort of Q function for the optimal policy must obey. Right? It says when I take an action in a certain state, it has to be the best one, the one with the best long-term payoff. So again, what you have here is a system of fixed point equations in this Q function. And so, one popular method people use to learn policies or perform reinforcement learning is you try to solve this fixed point equation, again, from noisy measurements, and then you can easily recover an optimal policy from it. Right, so this is a nonlinear system of equations now. But again, executing this, trying to solve this system of equations is called like temporal differencing or Q-learning in this case, in this specific context. Okay, good. So where does the randomness come in? So let's just be perfectly clear about this. So this is like what we're after. If we're, again, going back to this policy evaluation problem, I want to know what the kind of long-term reward is for being in a certain state for a fixed policy. I can, I have this fixed point equation. I could think about iteratively solving it this way. That's great, except usually I'm not given this model, like this P matrix and this R matrix, right? What I'm given usually is samples. So I get observations of state trajectories under my policy that I have. And I'm also given, this observed data should also include rewards that I have, right? And so what you're doing instead is you're not quite performing this iteration. You're performing an iteration that's based on a single sample. And essentially what you're doing is you're taking this function and you're drawing a random sample from it according to this distribution. Right, and so really what you have here is you have an observation of a random variable with this as its mean, right? Actually, it's really as h of dt as its mean, right? And so this falls exactly into our stochastic approximation framework, right? So if I just give you observed rewards and I update this value, the long term, my approximation what the long-term value is of being in each state, just according to this this equation. This is called temporal differencing. This corresponds to doing exactly stochastic approximation, where again this h is some kind of like a linear operator. So the noise in this case, it's not like you're generating vectors and adding noise to them. It's really that I have a distribution, and that distribution has the right mean, and I'm just drawing a sample from that distribution. So again, the same, like as in many places in machine learning, kind of the noise comes from having samples instead of having access to full distributions of things. Okay, so that's exactly where stochastic approximation comes into play, and how it relates to reinforcement learning. Okay, now I just want to state at this point that these types of iterations, they are related to doing things like stochastic gradient descent. But even in this simple problem, like almost the simplest problem reinforcement learning, you can't interpret H as a gradient map, right? It's some matrix which isn't symmetric, right? So it can't. So the Jacobian of this map isn't symmetric, hence, and so it can't be a gradient map. So what the consequences of that, you don't have quite the same structure you have when you analyze optimization programs, because I can't interpret this as the gradient of a function, right? You really need to more think of it as a dynamical system. Okay, so I'm just reinforcing that this isn't the same as doing stochastic gradient descent. It is kind of a different thing. Okay. Last thing, I'll go very quickly through this last sort of ingredient is this idea of a function representation, right? So when we have state spaces, these state spaces can be huge, right? I just showed you that drone example where the state was a picture, right? And so the space of all pictures is huge. The space of all configurations of the Go board is huge. Even like when I have like robots moving around and they have positions, right? That's even technically an infinite state space, even though it's simple. So you need a way to parameterize or simplify these things. And one way you can do it is the way I guess we're very familiar with is you basically take this function of S and you parameterize it by theta. And the sort of natural way, first way to do this, simple way to do this, is you say, okay, my model for this function is it lies in some subspace. That subspace is spanned by some basis vectors. So, some number of k basis vectors. And so my parameterization for this function is just these k, basis coefficients I use to build up this function, right? Again, that's a very natural idea. People like me from like harmonic analysis and signal processing, we tend to talk this way in terms of like basis functions and expansions. People in machine learning, they tend to talk a little differently. They talk about, okay, you have the state, you have some nonlinear map of it, and then you take a linear function, all of that nonlinear map, but ultimately it's the same thing, right? So it's whether or not you think of things in terms of the columns of a matrix or in terms of the rows. Okay, so, obviously, you can just think of this as I'm trying to solve for this theta that parameterizes this value function. And you might have competing constraints because you have this Bellman equation that says you need this, solve the optimal value function needs to obey this. You have your implicit constraints that your value function needs to be in the subspace. There's not, these in general will conflict with one another. But again, there's kind of well-known stochastic approximation algorithms that, again, sort of classical by this point results that they converge to sort of near optimal, like almost best approximations to these value functions. Okay, so that's again how maybe how function representation plays a role in this. In sort of modern systems, maybe you don't use a basis representation, maybe you use some kind of fancy neural net, but the idea is basically the same. You have some class of function that you're parameterizing with this parameter vector theta. Okay. So let's talk. So now that's all great, and those are all like interesting problems that have been worked on for 20 years or more. Let's what we're kind of doing new here is again thinking about this from the perspective of multiple agents. So this last kind of ingredient that we have which again is just related to fixed point iterations. It gives us this last ingredient. It gives us this idea of like multiple agents collaborating with one another. Okay, so again, we can talk about this not in the context of reinforcement learning, but really just in terms of like maybe what's the simplest problem in network science. So here's the problem. I have a graph, right? This graph over here is what's pictured over here. So each node has some neighbors. So here is node I up here at the top. You know, I've colored in its neighbors in blue. So not all, you know, this graph is high connectivity, but not every node is connected to every other node. Right, and here's the sort of the game I want to play. You know, what I want to do is I give each of these nodes a number. And what I want to do is I want them to cooperate to compute the mean of all the numbers, the average of all the numbers. Right, and so, you know, if this was a fully connected network, it would be easy. Everyone can just tell each other their numbers, and then you can just compute the local sum, and then everybody has the solution. You know, if not everyone's connected to everyone, you can, you can imagine some kind of like complicated networking protocol where, you know, I have to wait like 3 hops to hear from this person, and then I have their number and I can integrate it in. But actually something much easier works, right? All you do is you just communicate with your neighbors, right? And you take a weighted average of their numbers along with your own, right? And then you just update your state to be that. And you just do that over and over again. So I have my number, I locally average with my neighbors by communicating. I update my number to that average. And then I do this average again, updating my number, right? So you get this kind of diffusion process, or exactly this diffusion process on this graph. Okay, so then again, how you model is kind of the easy linear dynamical system. Like if V is the vector of numbers, and you know what I'm after is the average of the initial state. What I can think about this is how these numbers are updated is I apply this doubly stochastic matrix to this VK, where again, you know, the structure of this matrix is I'm just sort of, you know, the non-zero columns in every row corresponding in row I correspond to connections to agent I. Just make sure that the rows and columns sum up to 1. Then this has some very nice properties, right? So again, linear dynamical system, and we can solve it by basically using, again, this fixed point. So I just apply this W over and over again. So these are fixed point iterations. How do I know it's a contraction? How do I know it works? It's actually very easy. So again, here's the dynamical system. What I'm after is the mean. So, so basically the average of all these initial numbers that I have. So X bar times 1, I want everybody to have the same average ultimately. So I subtract that from both sides. This happens to be an eigenvector of W. You kind of know that since I'm taking weighted averages of things that are all the same. Of course, I get the same thing back. It also happens, so I can pull this W side here. It also happens to be the eigenvector corresponding to the largest eigenvalue. So the largest eigenvalue in this case is 1. Again, that's a classic result from numerical analysis. But basically, what this means is this norm of this error, right? This is not going to be any bigger than the second eigenvalue of this matrix W, right? The second singular value of this matrix W. And that is basically because this is sort of, I'm subtracting out the projection on the first one. So this is completely governed by the second singular value. All right, and so then this is just less than sigma 2. We know sigma 2 is less than 1. So we have this as a contraction method. So I guess the idea here is these nodes reach consensus quickly with this very simple algorithm, just kind of local communication, local averaging, 1 hop. You know, I only keep track of things that I'm learning this round, etc. And the key kind of quantity here, how quickly it is, it depends on, you know, the smaller this second eigenvalue, the better. I mean, this is referred to as the spectral gap in pretty much everywhere in the applied mathematics literature. And what you can, like, you know, it's roughly a measure of the connectivity of the matrix. So graphs that look like this, they tend to have larger values of sigma 2. Graphs that look like this, they tend to have smaller values of sigma 2. They mix quicker, if you will. Okay, so again, that's a very simple concept, but it's kind of the last ingredient to what we want to do. So we have this kind of like, you know, dynamical system with noise to do this stochastic approximation. We have this dynamical system idea to do consensus. So let's just look at like one problem we can apply it to. All right, so here's our first problem of multi-agent reinforcement learning. And here the setup is we're going to have multiple agents all working in the same environment, right? And there's one sort of joint state which describes this environment. but they each can take different actions. They each get different rewards. And what I want to do is I want to solve this policy evaluation problem. So, you know, each of these agents, they each have their own policies. I want to say how, for the overall good, like how good is this policy? And of course, like the states can overlap with one another. So they might be doing the same things in the same state. Okay, so again, here's the setup. So we have n agents. They're arranged on this kind of graph this graph basically represents how they can communicate with one another. You know, you can think of this like this example on the lower right here is like we have like a team of robots that's maybe trying to cajole this square to get into the circle, and this square reacts with some dynamics to the positions of the robots, and they want to figure out how to behave so that they can surround this guy and bring him back here, right? So there it's like, you know, we all have a common state, which is where is everybody and where is this square and where is this circle? But we can all take different actions, right? And maybe we see different rewards, right? Like maybe these guys bump into each other, you know, et cetera. Okay, so again, we want to evaluate the policy. So we saw like, you know, if we use, if we do these value relations, that this is basically a linear stochastic approximation problem here. Here, what we're after is the same idea of long-term value, but it's the long-term value averaged across all of the agents, right? So we want to know, you know, this policy might work better for some agents than it does for others. So I want to take that sort of all into account. Okay. So so like, you know, we're after here, so we have kind of the analog of the Bellman equation. But how we solve this ultimately is, you know, we don't do the exact same type of fixed point areas. What we do is we say, okay, I'm going to have this same type of, you know, we're using like this idea of like linear function approximation, but really all we're doing is we're doing the same type of like stochastic approximation iteration given an observation of a reward and a state transition. But we're also going to, so that's how we, you know, we update our local parameters, but also at every step, I'm going to share my parameters and average them. So I'm combining, this is a direct combination of this idea of local consensus, and then, you know, well, local meaning communication with my neighbors and doing consensus there, and then completely local improvement on what I think the value function is, right? So I take this average, and then I update by taking that average and adding in the innovation from my local observation. Again, you know, there's a, you know, a precedent for algorithms like this in the distributed optimization literature, where, you know, I'm trying to minimize a sum of functions, and I average what everyone thinks the optimal value is, or all of my neighbors think the optimal value is, and then I take a gradient based just on my function. And then you can show that convergence. So again, this is a lot of the same idea, except we don't have the same structure that we have of like gradients of a function. Okay, so that that's the sort of algorithm for temporal difference, the distributed temporal difference learning. Now we want to know how well it works. This is where the complicated probabilistic analysis comes in. There's, you know, again, sort of a beautiful subset of results, especially, but surprisingly recently in the centralized case of how long does this take to converge? So, you know, even as recently as 1 or 2 years ago, people were just figuring out, okay, if I have independent noise, right? If I make observations, if I restart this process every time, how many sort of iterations do I need to run to learn this policy value function? You know, when we're observing a string, a trajectory of what's going on, the perturbations, they're also dependent from iteration to iteration. It's a massive headache. So the noise itself is Markovian, and that it has to be handled. And there was sort of a Shrikant and Ying and Bandari. They put forth kind of a framework for how you can handle this idea that the noise isn't independent. So just simply averaging it out, you don't know exactly what's going on there unless you're careful. Okay, so then there's sort of lots of times people have written down this probably a multi-agent reinforcement learning, but no kind of conversion rates results like the type we've seen in the centralized case. Okay, so here's what we've sort of learned. What we contributed to this in a recent paper, and it's that okay, if I do this centralized kind of this consensus temporal difference learning, so this consensus stochastic approximation, And let's say I just use a fixed step size. I can again converge to a ball whose radius depends on that step size, and I do so exponentially quickly, right? And again, what's the important parameters here are like what the network connectivity is, right? The time penalty I pay is something like the mixing time for the underlying Markov chain. I realize I'm being very loose here and sweeping things on the rug. I'm just trying to give you an idea of what goes into the main results. And other things that go into the main results are things like the number of nodes and then the kind of nature of the other parameters from this Markov decision process. Okay, so we can say that. So that's that. So again, that kind of tells you that when we do this, all the agents, they converge to some balls around the optimal solution. That's already something. It's nice because it's fast. And then you can also refine the analysis that says, okay, if I damp these step sizes out, I can, I get rid of the network connectivity exponentially quickly, and then I get a 1/t convergence rate. And basically, this matches the result in the centralized case. And it also matches the result in the independent noise case, but up to this logarithmic factor, which that factor again comes from this kind of penalty you need because two samples of a Markov chain, if they're taken far enough apart, they can essentially be independent. But if they're taken right next to each other, then you have to be careful. So that's where these kind of logarithmic penalties in time come from. Okay, so that's one result. We also have and that, again, this tells you converge to this point. We also have like a general, not since this temporal difference is basically you're doing stochastic approximation, but it's a linear system. We also have a general like nonlinear result that, requires the functions at each node to be like strongly monotone and Lipschitz in the right way. And you can basically, take results and we get the similar type of like, if I do this at fixed step size epsilon, I converge to a ball of radius about epsilon at a linear rate, and you can apply this result to certain types of distributed Q-learning. Basically, you can also apply to distributed optimization problems that work with like Markov, sample to gradients through Markov chain Monte Carlo, etc. But for right now, just know it's not just about doing like stochastic linear approximation. You can also have nonlinear problems that work. Okay, so finally, for my last few minutes here, I want to talk about sort of a move away from stochastic approximation a little bit, more solidly into the realm of distributed optimization, but it's sort of distributed non-convex optimization. And in this problem, we have a similar type of scenario, but the idea is we're going to have teams of agents, but let's say they're each interacting with different environments. Right? So each agent sees, in this case, we'll just say one environment, but it could be a subset of these different environments. But we want to train all the agents to learn in how to act in all the environments, right? So it's kind of like, I only see data from one of the things I want to learn about. So of course, if I just optimize from that data, it's going to be different than if I saw all the data at the whole time, right? And so, what we're after here is saying, okay, let me try to find an optimal policy. Right. So given I have observation of environment, let me find an optimal way to behave where, again, I have one agent explores each environment. I have this idea of agents can locally communicate with each other. So maybe they're exploring different parts of an indoor area and they can communicate locally with one another. And again, what I'm interested in is performance guarantees. So this would be like, how many times do I need to update the policy to get to convergence? So we're not going to talk here about sample complexity, like how many observations I need to make. We're going to sort of say you make many observations, and we're just going to talk about how quickly you update this policy. So there are two examples we'll work through here and show results for. One is like, okay, a simple thing where you have a series of mazes you want to learn to navigate using a single policy, using the same rules. The mazes have different barriers, which are these red squares, and reward places, which are these circle dots. I'll show you some pictures later. And then also like a more fancy thing is you have these drones navigating this different indoor environments. And I want them to learn from each other so they can all learn to operate in their own environments. Okay, so again, we have many of the same ingredients. Usually when problems like this are formulated, when you're looking for this kind of optimal, like when you're now directly searching for a policy instead of just evaluating how good a certain policy is, it's oftentimes beneficial to search over the space of random policies. Basically, that gives you kind of a convexification. I can search over the unit simplex. You know, it's a basic fact that in single agent optimization, policy optimization, there's always kind of a deterministic policy that's optimal. In multiple agents, and this problem I set up here, it's not always the case. That's not something I'll talk about, but it's one of the surprises and one of the things that separates a problem like this from the single agent case. Okay, and so then we judge a policy in the same way. It's like, okay, if we generate an initial state at random, and then look at the reward sequence generated by applying that policy repeatedly, and then I sum across this long-term reward in each of these environments, I want to find the policy that maximizes this long-term reward. Okay, so because I'm running short on time, I'm going to maybe just focus on the important details. You need to regularize this problem, otherwise it doesn't work. Even the single agent case, the problem is non-convex, right? So it's this hard optimization program in general. You can find global optima using, you know, the analog of gradient descent under certain properties of the Markov process you're looking at. So these sort of exploration conditions that were set out beautifully in this paper by Agarwal et al. In the about a year and a half ago. Okay, and then, you know, for us, we have the multiple agents have competing interests. So the global solution is going to be suboptimal for all these different agents. So we know we're going to have constant consensus communication to make sure that people don't over specialize to the particular areas of interest. Okay, so in general, this is not, again, something we'll look at, you know, the gradients, you know, even though this is, you know, the first problem is not this. Second thing is also noisy. So if I'm learning from observations, I can't even compute these gradients exactly for large or only partially specified problems. Okay, so our result is like, you know, the framework we use is similar to the framework we used before. Like what we do is we say, okay, you know, each agent has this sort of this long-term reward that it has based on this, this should be a theta I, that it has based on this this current parameterization of the policy it has. So, you know, what I want to do is I'll do basically consensus gradient descent on this, where I average together my policy models from my neighboring agents, and then I take a gradient step, right? So I'm not just doing gradient descent, I'm also sort of perturbing in this average way. Sorry, this should be an equal sign here. There's a typo here. Okay, so that's again, it's the same kind of simple thing we saw in the kind of distributed stochastic approximation. Okay, so, and you know, what you can do is there's a way to compute gradients for the long-term reward, again, based on this Q function as value function. So you can imagine if you're doing this stochastically, estimating these functions can play a large role. For the particular result I'll flash on the next screen, we'll just assume that we can compute these values explicitly and hence compute these gradients perfectly. Okay, so again, sorry, there should be an equal sign here. This is theta ik plus 1 equals this. So what we can say is like, okay, for small enough step sizes, again, small enough depends on many different of the problem parameters. Basically what I get is I get convergence to a stationary point at something which looks like 1 over square root of k, right? So this is, I think, a result that's, you know, I won't say standard, but you know, if you know something about like optimization, non-convex optimization, you would guess this is true before you try to work it all out, right? And so what, you know, what's interesting here is the graph properties, you know, because the diffusion happens at so much of a faster pace than the kind of convergence of the gradient descent, the graph properties only play a role in the term that goes to 0 more quickly than you know, than the other constants like the regularization parameter, the number of agents, and the other MDP properties, the role that they play. Okay, we can also say that, you know, there's again, it's a mathematically complicated, like equal exploration condition that basically says, like, you know, if I can sort of guarantee that states that overlap between separate agents, I can guarantee there's some kind of equal exploration there. Then I can actually talk about, even though I'm non-convexity, I can talk about convergence to a global optimum. And again, this happens at this 1 over square root of k rate, right? So that's really nice. You know, the analysis is very delicate. Again, a big part of it is handling this non-convexity. The drawbacks here is, again, things are very delicate. You have to very, very carefully treat this regularization parameter. This equal exploration condition, it kind of makes sense intuitively, but it's really hard to verify in practice. So it's definitely a room where things can be improved. And we can talk about stochastic convergence where we're not observing true value functions, we're only estimating them. But we can't yet do it with finite sample guarantees. You can definitely talk about convergence asymptotically, but we don't get the same finite sample rate. Okay, so those are the sort of drawbacks of what goes on. So just some cool, like let me switch my screen here just to show you some videos. Okay, good. Hopefully you can see this. So here's just an example of, this thing in action. So we have 4 different agents here trying to navigate this maze, right? So this guy, if he was just acting on his own, he would just sort of learn to go down here and take this shortest path to this reward. But because different agents have rewards all over the place, you try to learn a reward that's optimal for everyone. And so ultimately you get a policy which sketches out this path here that you see on the lower right that hits all the, hits them all, but not necessarily for each one. It's not necessarily the fastest path. And this picture down here, this is just a picture of the policy parameters all converging to the same thing, right? So this is just a simple example which lets you know it does something reasonable. Here's like, you can have like conflicting goals where basically, if I have the shortest path, there's actually an obstacle in that way that I very much need to learn to avoid. So in this case, this guy, right here, rather than again just going down here, learns to go around because that's what these other people need to do to avoid their obstacles. There's also cases where there's conflicts, but they're not resolvable. So not everyone's going to be happy, right? That happens when there's a barrier and a reward on the same thing. So all this says is that does something. This weighs them off by having 3 agents be able to get their reward, but this guy, is just SOL. And someone's going to lose in this situation, and it happens to be agent 4 down here, or agent 3 down here in the lower right. Okay, so then like maybe, oops, sorry. Let me share again. Another kind of cool, so right, these are these examples. So another kind of cool example is like we have this again, we have this idea of like multiple drones exploring the same indoor environment, right? And so in this case, again, oops. Sorry, I'm switching back and forth here. The sort of the things you're seeing and the dynamics you're seeing in each of these environments is different, right? But again, we want to learn to navigate all of these, right? And so the goal here is to again, even though each of these guys is seeing different things, it has even a different state space because these pictures have a different nature. We want to learn a common policy. Okay, so what we do in this case, again, we'll switch for the last time, switching back. Is we do this distributed policy optimization. So then, what I'll sort of end with here is a numerical experiment, which brings up a very interesting research question. So when we do this, here we sort of measure the mean safe flight. So how long it took one of these agents to clash, right? So, what this table on the right here says is, agent 0, it could achieve a long-term reward of 15 trained in agent 0. And of course, it was a disaster when it applied to the other agents. And then likewise is true for agents specialized in environment 1 and agents specialized in environment 3 and 2. Like this sort of matrix is very heavy on the diagonal and terrible off diagonal. What's interesting is when I do this sort of distributed policy, not only do I learn a policy that behaves well, it actually behaves better than the specialized policy itself, right? And so this is, of course, an artifact of, you know, we have a limited amount of time, so things are noisy, so we don't converge exactly. But I think it brings up a very interesting question. It says, like, even though these guys are trying to learn different things, they help each other tremendously at the beginning with communication, and they converge very quickly to something that's reasonable. And much more, this data sharing helps them, even if they had ignored all their, all their neighbors, even though their neighbors are trying to learn different things. So usually we think of that as interference and compromise. Here it's explicitly helping you. So learning why this is true and trying to understand that from a mathematical framework, I think, is a very interesting mathematical question. Okay, I'm way out of time. I'll thank you for your attention. Here are publications related to this research. And of course, I'm very happy to take any number of questions that you might have. Thank you.